Hello everyone, welcome back to my channel Gyan Sampada, and today we are going to continue with thin film physics, which is a concept of condensed matter physics. So in our today's class we are going to discuss about the thickness measurement techniques. Till our previous classes we discussed how to deposit a thin film and what actually is a thin film, and now we are going to find out about the thickness of the thin film which will be formed by different deposition processes. So in thickness measurements we are having different approaches. One is electrical method or electrical approach and another one is optical one. So in electrical methods we have mainly two measurements. One is resistivity measurement and second one is capacitance measurement. That is, roughly we can say, if we calculate the resistivity using some formula, we are going to find out the thickness of the thin film, and in the same way under electrical methods we are going to find out the capacitance using certain setup, and using the capacitance value we will find out the thickness of the thin film. And second approach is the optical one, that is related to light or photons. So under this approach we are going to consider two methods. One is the optical absorption and second one is optical interference. However, there are different approaches, but I will be focusing mainly on these four important approaches under which there are some different calculating techniques. So today let us concentrate our studies in electrical methods. So first let us study about the film resistance. So this electrical method is applicable to metallic and low resistivity semiconductor films, which rests on the fact that the resistance is related to the film thickness and also the mean free path of the charge carriers. So if we understand about the resistance of the corresponding thin film, by calculating using different formula we can find out what actually is the thickness of the film which we have deposited, and this is applicable for metallic and low resistivity semiconductor films because they are having a resistance in a range and it is not very high. So an empirical thickness resistivity relation describing the polycrystalline films may be found out experimentally, and the same can be used to deduce the unknown film thickness. How? Let us see later. But the situation is complex in ultra thin and structurally discontinuous films, so that no reliance can be put on these resistance methods while calculating the thickness of such thin films in ultra thin thickness region. So this method is not much reliable and it is not applicable for different types of thicknesses of the film. And as resistivity of the semiconductor films is very sensitive to deposition conditions, this method is applicable only for comparison of the film thicknesses rather than absolute measurement. So when you just calculate the film resistance or resistivity, we can just compare it with respect to different types of films or the films obtained from different deposition processes, but exactly we can't say the film deposited by CVD process that is named as film 1 is having this much of thickness accurately. So a number cannot be determined, however we can do a comparison between different films. So let us understand how the calculation is done. Resistance of a metal film can be measured easily by making the film one arm of the DC or AC Wheatstone's bridge. So here easily we can observe the rough idea how it is going to work using the Wheatstone's bridge, and we know Wheatstone's condition or Wheatstone's bridge is helpful in determining the variable resistance, that is 3 out of 4 resistances will be known, and by the Wheatstone's balancing condition, which is in the form of ratios, we can just find out the other unknown resistance for the balancing condition. So for a given value of ratio of the arms of the bridge, the film resistance is proportional to the variable resistance, which can be measured by recording the potential across it, and the potential will be calculated from the circuit itself, and the R whatever you can see in the diagram, it is the variable resistance. So the variations of the bridge circuit can be employed for recording the resistance changes by changing the value of the ratio arms, and the variable resistance may be set to a value corresponding to the certain film thickness, and when the bridge will be balanced, a relay may be energized to actuate the magnetically controlled shutter to interrupt the vapor beam, and finally then shut off power to the vapor source. So it is simple. The film which will be deposited or depositing, it is having its own resistance. So whichever film thickness we need, corresponding resistance can be calculated and it will be set up. And when there is a balancing condition, at that time the relay, which you can observe in the diagram, will be energized, which is connected to the shutter where the interruption takes place, and finally there will be power shut off, that is closure will take place, and finally we are getting a comparable thickness of the film whichever we require. Coming to the accuracy, it is approximately 1%, that is accuracy in resistance, and due to the limited reproducibility of resistivity thickness relation used, accuracy may not be better than 5% also. So this is a crude way to find out the thickness, and that's why we just saw that it is mainly used for comparison purpose and not for accurate calculation of thickness. And the simultaneous measurements of the resistivity and the Hall coefficient, that is rho and RH, in a thin film, especially thin metal films, can be utilized to determine film thickness from graphic solution of their size effect equations. So this is a rough idea based on the resistance how thickness can be tuned. Coming to the calculation part, there are different approaches which are given by different scientists or physicists, and first approach was given by Van der Pauw, and I am just naming it as Van der Pauw method. So we will be discussing about main three methods where we are going to find out the relation which is going to connect thickness with the resistance or resistivity. So an excellent method which can be used for in situ measurement of both resistivity as well as Hall coefficient of metal as well as semiconductor films is due to Van der Pauw. And using the reciprocity theorem, he showed that if A, B, C and D, let us say, are any four sufficiently small ohmic contacts which are arranged successively on the circumference of the film of an arbitrary shape, then resistivity will be given as 4.53 into T, which is the thickness, into R ABCD plus R BCDA divided by 2 into F of R ABCD by R BCAD, and unit will be ohm centimeter. So let us take it as equation number 1, and clearly we can observe that we are having the relation between the resistivity and the thickness. And what actually are this R? So this R AB comma CD, it represents or denotes the resistance between A and B when current is passed between C and D, and RBCDA is resistance between BC, that is B and C, and the current is passed between D and A. So that is how it is denoted with respect to the Wheatstone's network, where we are taking four resistances A, B, C and D. And this F is the correction factor calculated by Van der Pauw, which is equals to 1, that is unity, when the numerator is equals to the denominator. So when these two terms are equal, that is f of 1 is going to be equal to 1, and that is called as Van der Pauw correction factor. And this is the equation to find out the resistivity in terms of the thickness. And another term is the Hall coefficient, which is RH is equals to 10 raised to 8 into T by H into delta R of BD comma AC. So again here we can relate Hall coefficient is depending on thickness of the film which is deposited. And according to Van der Pauw, if we just consider the resistances as equal, then we can just say that RH is again equal to 10 raised to 8 into T by H into delta of resistance with respect to AC, while current is passed between B and D. So both are going to be the equation where we can find out the Hall coefficient, and this will be again equal to mu H into rho, where mu H is the Hall mobility, generally in the units of centimeter square per volt second, and rho is the resistivity which can be found out using equation number 1. So delta represents the changes due to the applied magnetic field, that is H, generally in Gauss. So this is the approach given by van der Pauw, where we can tune the setup, where we can find out the thickness or resistivity and Hall coefficient finally in order to get the thickness, or whichever thickness we require that can be set, and accordingly we can find out the corresponding resistances. Coming to the second approach is given by Lange, and that's why I am naming it as Lange's method. And Lange analyzed an infinite sheet method and a circular sheet method which do not require contacts at the edge of the sample. In the previous method, the resistances or the contacts in order to find out the resistance was at the ends of the thin film, which you can clearly observe in the previous diagram. But Lange's method had no such restriction, and the difference was that in this approach the contacts were at the center. That is, by placing the 4 contacts at the center of the specimen, Hall coefficient is going to be calculated using the same equation, that is equation number 2, which we have seen in the previous slide. Only difference between the first approach and second approach is that the placing of the contacts. In the first approach given by van der Pauw, the contacts were at the edge, while in Lange's method the contacts were at the center of the film. But the condition is that the interspacing between the points has to be small when compared with the size of the specimen. Points are nothing but the contacts which we are going to utilize for measuring the potential or giving the current to the specimen in order to find out the resistance out of it. So those points and the distance between those points should be less when compared to the size of the specimen or the thin film. That is the condition in Lange's method. Then coming to the third method, which is nothing but the Wales method, or even you can say it as a 4-probe method, which is generally used in order to find out the potential or the resistivity of any sample. So most widely used method for measuring the resistivity in the range of 10⁻³ up to 10⁻³ ohm centimeter was given by Wales, and he employs the collinear 4-point probe with equal separation between the points. That is, here we can observe that there are 4 contacts which are having the tips or points, and this is the specimen or the thin film. Here the 2 probes which are at the center are going to measure the voltage across the film, whereas the other 2 probes or contacts which are at the periphery are going to measure the current. Those are nothing but the current probes, and each probe will be having distance, let us say S, and they are having the equidistance between the probe. And again the same thing, the distance between each probe is going to be very less when compared to the size of the specimen. So this is in general the 4-probe setup. So if you find out the voltage across the film for a given value of current across the thin film, then easily you can find out the resistance, and finally we can find out the resistivity. So if I is the current passing between the outer points and V is the potential drop between the inner points with the point spacing S, then the resistivity for the specimen of infinite volume will be given as rho is equals to 2 pi S into V by I. Let us call it as equation number 3. And if the specimen dimensions are comparable to the point spacing, that is whatever parameters will be there, if it is length or so, if it is comparable or similar to that of the spacing between the probes, then the resistivity for various geometries and also for different types of boundaries will be given as rho is equals to 2 pi S V by I into F of L by S. So L is the distance between the nearest probe and the limiting boundary, that is with respect to the specimen we can just say as length, and F is the function for several possible cases which has been calculated by Wales and Euler, that is VALDES, Wales, and Euler, UHLIR. So these two have given certain data which are going to give us several possible cases or values for F which have been already calculated. That is, when you take the ratio of these Generally for any experimental setup we can take S values as constant. Let us say S value is 2 millimeter, and for different lengths when you take the ratio, what is the value for F of 0.25 or 0.5, 0.75, all these values are already calculated by these two physicists. When you substitute the value of F, easily resistivity can be found out. And the useful simplification of collinear probe relation, that is equation number 3, obtained for thin specimen, that is if thickness is very less when compared to the value of S by 2. S is nothing but point spacing, and if you divide it by 2, that is if the film thickness is only this much amount, then for that case the resistivity will be given as 4.53 into V by I into T, where T is the thickness of the film, but the condition is this: T should be very much less than S by 2. So if you just rearrange this, we can get the relation where resistivity and thickness are related to each other, that is rho by T is equals to 4.53 into V by I. V is the potential or voltage divided by the current which is passed through the probes across the thin film. So this is the relation which gives the sheet resistivity of the film. So these are the three main approaches where we can find out easily what is the resistivity. Once you find out the resistivity, Hall coefficient and other things are going to be calculated very easily. So finally this relation is very important, that is used for measurement of thickness using the film resistance using 4 probe setup. So this is one electrical method, that is using the resistivity measurement. Coming to the second method is the capacitance monitor or capacitance measurements. So in this case, the thickness of the dielectric films mainly may be determined by directly monitoring the capacitance of a capacitor configuration of this type, which we can observe in this diagram. So Keister and Skipple constructed a capacitance monitor plate by depositing aluminum films and then photo etching the comb pattern. So here we can easily observe the comb pattern which is created. So it is acting something like a capacitor. Then using 1/3 inch of silica monitor, using 1/3 inch silica monitor plate with 56 lines which is having the width approximately 0.0075 inch, approximately the capacitance of 65 picofarad was obtained. So that is using the setup which was designed by Keister and Skipple. And with respect to the difference in the thicknesses, the capacitance values were also going to change. That is, a 10 micron thick deposit of silicon oxide increased the capacitance of the film by about 13%, which is again significant. So by this only it is clear that with respect to thickness, obviously the capacitance is also going to change. That's why it is used in order to measure the thickness of the film which is deposited. And then another scientist named Riddle, he measured the rate of evaporation by measuring changes in the capacitance of a parallel plate condenser, which was due to the changes in the dielectric constant resulting from the presence of vapor of the evaporant. Whenever evaporation is going to take place, because of the vapor, the dielectric constant was going to change. And dielectric constant we know easily we can find out using the capacitance, that is epsilon r is given as C by C naught. That is capacitance with respect to the medium to the capacitance in vacuum or air. That's why it was clear that capacitance is somehow related to the thickness, and if the capacitance is measured, dielectric constant is going to be calculated, using which we can easily find out what is the thickness of given dielectric material or any thin film. But the main thing is that the method is not sensitive and requires careful measurements, and it may be subjected to spurious effects due to the stray electrical charges in the vapor or in the vacuum chamber. So if there are any impurities remaining in the vacuum chamber or whichever is created due to the electric charges, because capacitance is going to be linked with respect to the electric charges. So because of that, the thickness measurement is going to be interrupted, due to which we cannot find out exactly what is the thickness of the film whichever is deposited. So these are the two main methods which we use in order to find out roughly or accurately the thickness of any thin film. So in today's class we saw the first method, which is the electrical method, under which we studied two approaches. One was using the resistivity measurement and second was using the capacitance measurement, and understood how we are going to find out the thickness with respect to these two parameters, that is resistance and capacitance. So in our next class we will be dealing with the optical methods of measuring the film thicknesses. So till then, study well and thank you for watching.